Click the link in the description to download your own copy of this video's problem. Hey guys, Russ here. Welcome back to another fantastic chemistry video, and today we're going to talk about acids and bases. Using Ka expressions, explain the difference in the pKas of the molecules below. All right, well, there's a few things we got to cover here. First of all, pKa. pKa is negative log of the Ka, and Ka is the equilibrium expression for a weak acid. So generically, it's written like this. Okay, so there's a generic expression for Ka. Not a big deal. You guys already knew that, I'm sure. But let's talk a little bit about it. The bigger the Ka, the larger the Ka, the more acidic you are. The lower the Ka, the less acidic you are. So anything that can make the Ka larger promotes acidity. Anything that can make the Ka lower does not promote acidity. It promotes, non-acidity or basicity. Okay? So now, if we can make these two numbers large and this number small, you'll be more acidic. If these numbers are small and this number is large, you're less acidic. You're less prone to ionize. Let's say it that way. So let's take a look. We have methane with a pKa of 50. We have water with a pKa of 15.7. So water's much more acidic, like much more, by orders and orders and orders of magnitude more acidic. So that means water wants to ionize more than methane does. That's what it means. Let's take a look at the equilibrium expressions. All right, guys, so now I've written the equilibrium expressions for both molecules. All right, guys, so I've written the equilibrium expression for both molecules. And now let's write the Ka for the top one. Ka expression for the top reaction, the methane, is going to have hydronium plus methyl anion divided by the concentration of methane. And that's going to give us 1 times 10 to the negative 50. So that's a very, very small number. So that means the equilibrium of this reaction lies far to the left. Probably none of these at all in solution. Okay? It's far to the left. Far to the left. Not acidic, essentially. One times 10 to the negative 15.7. We could work that out to be a whole number exponent, but we don't need to. We just need to look at it and say, okay, that's much more acidic. Reason why is 10 to the negative 15 or 10 to the negative 16 is a much larger number than 10 to the negative 50. 10 to the negative 50 is infinitesimal small. 10 to the negative 15 is a heck of a lot more, heck of a lot bigger. Okay? Now that means a few things. That means, first of all, water is more acidic than methane. That's not surprising. None of this chemistry is surprising, I don't think, to any of you. But the explanation, I think, might be a little different than what you've heard. So let's take a look at the Ka expressions. In order to get this small number, these two numbers on the numerator had to be small. And this concentration, so the concentration on top is small, concentration on bottom is large. So this number is extremely small, minuscule. To get this Ka value, and comparing it to this one, is much larger. So via comparison, only by comparison, these two numbers must be much larger than these two. Must be. And this number must be much smaller than that number. Must be. Must be. That means something. What can we discern from this? Well, we can discern that the concentration of hydroxide in water must be a lot higher than concentration of methyl anion in water. That tells me that this anion must be significantly more stable than that anion. That's what it tells me. This anion must be relatively stable in comparison to methyl anion, which must be relatively unstable. That's what it's telling me. It's telling me something about the anions. Because the cations, let's face it, are the same for both reactions. So we don't really get much information from that. What we do get information on is the conjugate bases. This conjugate base, much more stable than that one. And why would that be? Because oxygen is more electronegative, and that's where the anion is sitting. The anion is sitting on the oxygen. Oxygen is more electronegative than carbon by a lot, so therefore oxygen is more able to accommodate a negative charge and be less reactive than carbon, for example. Carbon with a negative charge, highly reactive, totally wants to react, and it does. Okay, so that's how you would use Ka expressions. That's how you interpret pKa expressions, and that's also how you interpret the data once you have it. Okay. Now, guys, I hope you liked that video. If you did, slap that like button. Leave a comment below. Tell me what I can do to help you in your chemistry endeavors. Maybe I can answer a question personally for you. If you like my content and want to become part of the Dr. Betts team, go ahead and slap that subscribe button. Become a member of my channel. That would really, not a member, a subscriber to my channel, excuse me. Become a subscriber to my channel. It really helps out YouTube creators, including myself, to grow their channel, to get more reach, to help other people in need of chemistry help. So I really would appreciate your subscription. And with that, I want to wish you all good luck and good chemistry. We'll see you soon. Email drbetts@protonmail.com if you would like a copy of every problem in this series.